Okay, let's talk about line integrals. When we integrate a curve, integrate over a curve instead of over an interval, all right, we use what's called a line integral. And let's just start in R2 because it's something that's familiar to everybody at this point. All right. When we start with a curve in the plane, all right, we can parameterize everything in terms of t. So we start with a curve that is x equals x of t and y equals y of t. All right, so x and y are both functions of t, same t as usual. Or equivalently, we can look at this as a vector, right? Because once we have something parameterized like that, we can use our vector notation, r of t equals x of t I plus y of t j. Okay. Now, if this is a smooth curve, right? If r represents a smooth curve in the plane, then we can parameterize in terms of arc length, which means I can take the antiderivative of a function, f of xy, ds. Remember, s is arc length. And yes, I realize I'm dragging you guys all the way back to the beginning of the semester here. All right, so where s is a smooth curve, right? Right, where s is the arc length of a smooth curve. All right, now, so let me just again remind you, right, what is arc length? Well, arc length in R2 is just the square root from A to B, right, the endpoints of your arc of dx dt squared plus dy dt squared dt. All right, so if I have a situation that fits these conditions, then I can take what's called the line integral. Now, the line integral, we use c down here for our bounds, all right? We've been using, B for box, E as a R3 region, C we use for a curve. All right, and that C represents a line integral. So if I have the integral over a curve in the plane of f of xy, ds, forgot my ds. All right, we're going to look at that parameterized from A to B, again, the endpoints of the curve. F, the function, parameterized for t, so x of t, y of t. And then the differential becomes the arc length. So we have the arc length, right, dx dt squared plus dy dt squared dt. Okay. Now, this has the potential to blow up and become something that is really, truly nasty. So we're going to learn some ways around this. But there are some problems that can be done. There are some problems that can be done this way. All right, so since I kept myself to one side of the board, I'm going to write over here. All right, so in order to be able to do this, C has to be a curve that we traverse exactly one time from A to B. So we can't go back and forth. All right, it can't be a closed, well, can it be a closed loop? It might be a closed loop. But A to B if that's the case, if we have a curve that's traversed exactly one time from A to B, then the integral is independent of the parameters, all right, which is nice. It means it's something that we can probably work. So let's just say I have, let's do this. I have the integral over a curve, and the function I'm going to integrate is 2 plus x squared y ds. All right, where C, all right, C, right, our curve is the upper half of the unit circle. So it's the upper half of the unit circle. All right, now what that gives me is, and I like to graph my path. I always like to graph my path. It helps to see what's going on. All right, so the upper half of the unit circle is like this. Okay. All right, so when we traverse the unit circle, we always traverse it in the anti-clockwise direction, right? So that means my path is going this way. Okay. So when I do that, right, because my path is circular, I have to figure out how I'm going to parameterize, right? How am I going to parameterize this? Well, if my path is circular, then I'm going to use polar coordinates to parameterize. All right, so I'm going to use, since I'm on the unit circle, r is 1, so x is going to be cosine t, y is going to be sine t, and what happens to the arc length, right? So what is the arc length then? If I calculate the arc length, the derivative of cosine t is negative sine t. I square that, I get sine squared t. The derivative of sine t is cosine t. I square that, and I get cosine squared t. So I have sine squared t plus cosine squared t, which is 1. All right, so this is a situation where the arc length becomes the derivative of the arc length becomes a solid constant. Okay, which means if I'm going to do this over polar, right, then I'm going from 0 to pi, right, the top half of the unit circle, and I plug in my function becomes 2 plus cosine squared t sine t dt. Right? And again, it's dt and not all of this, because all of this is 1. So this is an integral that I can work out, right? This is just a u sub. All right. In fact, I'm going to leave that to you to work that out, because that's literally a Calc 1 integral right there. All right. Now, our path does not have to be singular like this. We could have a path that's piecewise. Okay, so if I have a path, if my C is a piecewise smooth curve, we can split the integral up as C is split up. Okay, so let's take a look at, not that, come on. All right, let's take a look at what that's going to look like. All right, so when I talk about piecewise smooth, I'm talking about a curve that maybe has breaks in it, right? That looks like this. Right, it could have many parts to it. The smooth part means that each individual piece is literally smooth, okay? But it also has to be continuous. So it can't be, I can't have a hole or a split, just these kind of bends to the curve. All right, and if this is the case, then I can break these up into separate curves. And then I can break my integral up, right? C1, C2, C3, C4, like that. All right, and just look at each individual path. So, for example, all right, if I have, let me see, suppose I have the antiderivative over C of 2x ds, and my curve C is going to be a piecewise function. So it's going to be y equals x squared from 0, 0 to 1, 1. And then it's going to be x equals 1 from 1, 1 to 1, 2. All right, so if I look at my path over here, all right, from 0, 0, actually I need more up there, from 0, 0 to 1, 1. All right, I'm going to have a parabola, so it's going to look like that. And then it's going to be x equals 1 after that, so it's just going to go straight up. All right, so here's the point where we split. So from 1, 1, oh, actually it doesn't go up that high. All right, well, let's just put 2 up here. All right, to 1, 2. Okay. That's more or less what our region looks like. All right. Now it could continue after that. It could have more, but that's where I'm stopping. Okay. So I have basically 2 paths that I have to transverse. All right. The first one is from 0, 0 to 1, 1, and this is my curve. So my first integral, all right, my first integral is going from, or for C, hang on a minute, that's not right. I'm actually doing it this time. So C1, right, C1, let's note it this way I won't get confused. All right, C1 is going to be from, because this is an integral just involving x, from 0 to 1. Right, from 0 to 1. And this is going to be 2x. And then I have to do the arc length, right? So the arc length is going to be the square root. Now, I have a choice here. All right, in terms of my parameterization, because I already only have a function of one variable, I'm just going to parameterize on x. All right, I don't need to do t here. So this is going to be dx squared plus dy dx squared. All right, dx. All right, so I end up with here the antiderivative from 0 to 1 of 2x times, I'm going to put that to the 1/2 power. Well, dx is 1. 1 squared is 1. Plus dy dx. All right. So dy dx is going to be 2x, right? Because y is x squared along this path. All right, so y is x squared, so dy dx is going to be 2x, and when I square that, I'm going to get 4x squared to the 1/2 dx. Okay. All right, so this ends up, again, just being a straightforward Calc 1 integral. All right, so do a u sub in here, work it out, evaluate it, and we end up with, what do we end up with? Wow, okay, we end up with 1/6, 5 to the 3/2 minus 1/6, whatever that is, okay? It's going to be the square root of 125 over 6. So the square root, yeah, that's really, there's no way to simplify that. All right, and then C2, all right, which is the second path here, all right, which is going from x equals 1 to x equals 1, right? So this one we have to do, does it make sense to do that, right? No, it doesn't. So this one's going from along y, right? So y equals 1 to y equals 2. Okay, so if that's the case, then when I set this up, I'm going from y equals 1 to y equals 2 of 2x, same thing here, only now what we're looking at is this path here. All right, so dx dy, right, because now we're parameterizing in terms of y. All right, so we're going to go dx dy plus, whoops, squared, dy dy squared dy. All right, so we have the antiderivative from 1 to 2 of, okay, so if we're parameterizing on y, then x is 1, right? That's our path there. Dx dy, the derivative of x with respect to y, is going to be 0 because that's a constant. So that's 0. And dy dy is 1. So that's 1. All right, dy. So we end up with the antiderivative from 1 to 2 of 2 dy. All right, so again, you can work that out. You're going to end up with 2. All right, so the total, right, the total integral over the entire curve C of 2x ds is going to be C1 plus C2. So it's going to be 1/6 5 to the 3/2 minus 1/6 plus 2. All right, and you can simplify that down. All right, line integrals with respect to x and y, right? We can replace the ds essentially with either x prime of t or y prime of t dt. Okay. Now, what we get here frequently, these will occur together where we have one with respect to x and one with respect to y. All right, so when we have those together, we've got a notation that lets us kind of combine or simplify what it is we're doing. All right, so let me write this again. All right, so if we have a line integral with respect to x and y, like this one was, all right, then the integral over c, f of xy dx can be replaced by, again, over the endpoints of the path with respect to x, f xt yt x prime dt. All right, same thing with y, right? So if I have over c f of xy dy, all right, that's going to be, do I want to use the same? Yeah, I guess so. We can use A and B again. Maybe I'll just say C and D, just to make them different. Yeah, okay, it doesn't matter. F of xt, yt, this time y prime of t dt. Okay, now when these occur together like they did in the previous problem, all right, what we do is we define two functions, p of xy and q of xy. All right, p of xy, q of xy. All right, and this oh no, not like that. Sorry. And we can do it this way. Right, okay, so curve 1 with respect to x, right, we say p of xy dx, and q over the curve of xy dy, which is really what all of this ends up being. All right, we write it as a single integral, right? So we have the line integral of p of xy dx plus q of xy dy. All right. All right, so if I have a situation where I can apply this, all right, so let's take a look at, let me see. Let's take a look at this problem here. I got a good one. I'm trying to pick and choose my problems carefully here. All right, so here's a line integral over c, and this is going to be y squared dx plus x dy. Right. And my curve, I'm going to give it to you graphically this time, which of course is always challenging. All right, is going to be, let's see, from down here, this point is -5, -3. And then I have a point up here, which is 0, 2. And then I have a curve, x equals 4 minus y squared, which is going to, okay, so that's going to come over here at like 4. And that's going to go this way. That's a parabola, by the way. Okay, and the direction that we're moving in is this direction. Okay, like that. Whoop, hang on. I just screwed that up. Let me just do that and I'll fill it back in. All right, so let me not put all the directions in quite yet. That's rounded there. Okay. All right, so we want to go from the point -5, -3 to the point 0, 2. And I have two different paths, right? One path is going to take me on a linear route from this point to this point. The other path is going to take me on a route along this parabola from this point to this point. Okay, so C1, let's take a look at C1. All right, we'll call this one C1 and we'll call this one C2. All right, so along C1, all right, how can I parameterize this in terms of t, right? Well, the easiest thing to do is going to be to write the equation where, let's say we start here, right? This is my starting point, and this is my ending point. All right, so I have to parameterize this in terms of t. All right, so as t goes from 0 to 1, so let's look at this. As t goes from 0 to 1, what are x and y doing? Okay, so what x and y are doing, well, I need to be able to get when t is 0. Right? I need to be able to get when t is 0. I need x to be -5, and I need, when t is 1, I need x to be 0. Okay, so think of it this way. When t is 0, x is negative 5, and when t is 1, x is 0. So I've got 2 points. I can write the equation of a line. So if I take those 2 points and I write the equation of the line, x equals a function of t, I'm going to get x equals 5t minus 5. All right, when t is 0, x is negative 5, and when t is 1, x is 0. All right, we can do the same thing with y. All right, when t is 0, y needs to be negative 3. And when t is 1, y needs to be 2. So again, I can take those 2 points and I can write the equation of a line. And when I do that, I get y equals 5t minus 3. Okay, so I'm able to parameterize this linear path in terms of t. So then I can write my line integral here all in terms of t. All right, so t is going from 0 to 1. All right, so y squared dx. So y squared, right? Here's y squared. I'm just losing my place here. Here we go. Y squared. So that's going to be 5t minus 3 squared. Dx, that's the derivative of x, so that's times 5, plus x, which is 5t minus 5, dy, the derivative of y is also 5, and this whole thing is now dt. Okay, so again, Calc 1 integral, just multiply this all out, do the antiderivative, you're going to end up with negative 5 over 6, all right, when you do this. All right, now the second curve is a little different, all right, because it's not a linear path, so I don't have that 2 points thing where I can just write these in terms of t, but I do have x is a function of y, which means I can parameterize this in terms of y. All right, since I'm moving along a function of y here. So when t is 0, all right, so when I go along the second curve, all right, when I go along the second curve, I want to see where is y going. So y is going from negative 3 to positive 2, right? So y is going from negative 3 to positive 2. All right, x is basically just a function, right? So x is 4 minus y squared, and y, well, it's just y. So I'm going to set this one up from negative 3 to 2, right? My bounds along y. All right, y squared dx. So y squared is just y squared. Dx is the derivative of this, which is going to be negative 2y plus x dy, right? So x is this, and the derivative of y is 1. And now all of this is dy. Okay, and again, this is just straightforward. Multiply it out. When you get the antiderivative of this, you're going to have 245 over 6. And what you're going to notice here when you compare your two values is that they're not the same. Even though I'm traveling from the same t0 to the same t1, same 2 points, I'm taking different paths, okay? So when you're doing line integrals, your answer is dependent on the path. Different paths are going to give you different numeric values. The other thing you have to be careful of is the direction that you're going in, right? If I take the antiderivative from this being t0 to this being t1, I get negative 5 over 6. If I reverse that path, going with this being t0 to this being t1, that's going to negate the integral. I'm going to end up with a positive 5/6. So the path you take and the direction you take makes a difference, okay, in how you deal with this. All right, now this extends naturally into R3. All right, so if we're over what's called a vector field, and I'll let you guys read 16.1. I didn't cover it in detail. Actually, I didn't cover it at all this time around. I don't usually cover it in detail in class, but you can read about vector fields. So over a vector field, we have a similar constraint. All right, F is a continuous vector field defined on a smooth curve, and that just means we have a vector function. Okay, and we can use what we did back in chapter 11-ish, I think it was, when we talked about work, right? Work is force dr, right? When we have a vector r. All right, so we can look at the antiderivative of work, right? So let me get a little bit of space here. All right, so if you remember back from chapter 11, we defined work if we had a vector function, r of t, right? Then work was force times direction, force dot direction, not times, right? And in this case, dr dt. Right, so if I have a vector function, right, if I have a vector function where t goes from a to b, right, a, t, b, all right, then the antiderivative over c, over a curve of work, f dr, right, f dot dr, is going to be the antiderivative from a to b of f of r of t okay, dot r prime of t dt. All right, so you'll notice r prime of t is our tangent vector. All right, so you can think of this a to b of f dot t, our tangent vector, or a unit tangent vector, ds. Okay, either way. All right, so if you need to find the work done by a force field, all right, and let's say that field has the equation f of xy equals, let's see, what do I have here? x squared I plus x, I'm sorry, minus, I put a minus in here, minus x, y, j. All right, and the particle is moving along the quarter circle. All right, so our particle moves along the quarter circle. Just the standard unit circle. Okay, so r of t equals cosine t I plus sine t j. All right. Then we can parameterize in terms of t, polar, right? R of t is already done. That's already done. All right, so f of r of t is going to end up being cosine squared t I plus cosine t sine t j. Right? R prime of t is going to be, let's see, so R of t, where was I? Oh, right over there. All right, so minus sine t I plus cosine tj. All right, and then we do f dot r prime, right? So f dot r prime, these are both vectors, by the way. All right, f dot r prime is going to be cosine squared t times a negative sine squared t. So negative cosine squared t sine t plus this dot this, which is going to be, again, right? Wait, how does that be negative? I'm missing something here. Hang on. I wrote something plus when it should have been minus right here. Okay. That should be minus because the function is minus. Right there. Okay, anyway. Plus a negative cosine squared t sine t. All right, so we end up with negative 2 cosine squared t sine t. All right, and that's what I'm integrating, right? So we're going over a quarter circle, 0 to pi over 2. All right, negative cosine 2t sine t dt. All right, and again, that's just a straightforward u substitution. And that is going to end up being negative 2/3. All right, so I'm going to, in the next video, which will actually be our last video, I'm going to extend this to Green's theorem, and we'll talk about that in the next video.